to this point, we've been kind of limited on the trig functions we could do integrals of. We could basically only do those trig functions that we had a derivative formula for. So we could do integral sine and integral cosine. We could actually do integral secant squared because secant squared is the derivative of tangent, but we actually couldn't do integral secant. We could have done integral of tangent times secant because that's the derivative of secant, but we couldn't do the integral of tangent. Well, now we actually have enough tools that we can work out the integral of tangent, because tangent can be written as sine over cosine, and then we use that idea, well, let's try and let u be the denominator. So let u be cosine of x, and then du would be negative sine x dx. So you see, variable-wise, we have what we need to go with our dx. We just need to have a negative sign there. So I can go ahead and rewrite as 1 over cosine, and then I put my negative sign with the sine x dx. And then because that negative sign come out of nowhere, it needs to go out front. And now we have our integral in the form 1 over u du. So we could write that down and then change that into ln of u like we did in the previous problem. Or we could just go ahead and jump ahead and say, hey, instead of writing ln of u, I can just go ahead and put in what u is, which is the cosine of x. And so we get the answer here. The integral of tangent is actually the negative of the ln of the absolute value of cosine of x, plus a constant. Now this time, the absolute value doesn't go away because cosine can be and is very often negative. So we need to keep the absolute value in this case. In a similar manner, you could do the integral of the cotangent function. Let's turn now to the integral of the secant function. And so, just like we did with tangent, we can rewrite that as 1 over cosine dx. And we might think to ourselves, well, let u be cosine x like we did here, but then we're kind of out of luck because what are we doing with that minus sign? Where's that going? What's happening there? Things aren't working the way we'd like them to do. So we're kind of like, now what? Now what do we do? We're kind of at a barrier where we're just not sure what to do. Okay, well, turns out that there is another way. And so the idea here is I'm going to multiply by 1. Multiply by 1 in a really strange way. But once we set this up, this trick will make sense. So I decided to multiply both top and bottom by secant x plus tangent x over secant x plus tangent x. So I multiplied basically by 1. I haven't changed anything. Right? I haven't changed anything. I've multiplied just by 1. And now in the top, that will give me secant, if I multiply through, secant squared x plus secant x tangent x all over secant x plus tangent x. And then we try and say, well, let's let u be the bottom. Secant plus tangent. Notice now when I do the derivative of this, the derivative of secant is secant times tangent. The derivative of tangent is secant squared. This trick comes from the idea that secant is a common factor of the derivative of both secant and tangent. So you could actually write the derivative of secant plus tangent as secant times secant plus tangent. And so that idea was really the key to making this work. And a similar approach works with the cosecant. So this is just something that you kind of have to remember here. And so then when we do du, as expected here, the derivative of secant is secant x tangent, which is the thing on the top. Bottom secant squared. And so then the top thing there, that is my du. The bottom thing is my u. So I basically have 1 over u times du. So you can actually write it out that way. 1 over u du. And then we can work the problem out. That's going to be natural log absolute value. And then we substitute un for the absolute value. Ln absolute value secant x plus tangent x plus a constant. And so now we have the antiderivative, that family of antiderivatives for the secant actually turns out to be the Ln of secant absolute value secant x plus tangent. And in a similar manner, by multiplying both top and bottom by cosecant plus cotangent, you could do the integral of cosecant.